Good afternoon, everyone. My name is Massimiliano Giacometti. I am a senior hardware designer at Hensoldt Cyber, and today I am here to present you our first chip, which is called MiG-V. MiG stands for Made in Germany, and the V is to remind you that we're talking about the RISC-V-based system. So what is MiG-V? It is a general purpose system on chip, which has been hardened with logic locking and is capable of running SEL4-based operating system. Why did we think that the market was waiting for a MiG-V? Because we think that the conventional IT solutions are vulnerable and the techniques which are generally applied to secure these systems don't pay off. They can be described with the expression patch and pray, which means that the symptoms are treated only after they arise. While our motto, secure IT instead of IT security, wants to underline that we want to provide a system, hardware and software, which is secure by design. So we don't have to run after attackers and patch things after we discover issues. Let's have a deeper look at how our hardware looks like. So first, what is the problem which we first wanted to secure? The problem is the one which regards the control of the production chain. Basically, without having full control on the whole production process, it might happen that an attacker at the foundry will be able to reverse engineer our system by looking at the GDS2 files which we send them. We'll be able to identify a meaningful location where to insert and hardware Trojan. Will be able then to corrupt our system and we will receive it. And we have to be sure that the system, the chip, the die we receive is the same as the one we are expecting. How it could be possible to detect a Trojan after production? One way could be physical analysis, but it is extremely costly. It takes a lot of time and it is also challenging. The other way could be testing, but when you have to test something which you don't know, there is a high risk to not detect the malicious circuitry. So the solution which we want to foster is the prevention of the insertion of hardware Trojan. How is this done? By means of logic locking. So the logic locking mechanism is explained in the figure on the bottom left. The leftmost half represents the original netlist of our system. The logic locking framework randomly selects signals in this netlist and it inserts on this path new gates which are controlled by new inputs for the circuit. So in this case we have the obfuscation gates, which are KG0 and KG1, and they are controlled not only by the signal, the original signals driving through the netlist, but also by new inputs K1 and K2. And only when K1 and K2 have the correct value, the functionality of the obfuscated netlist is exactly the same as the original circuitry. So when we ship an encrypted GDS2 file, and with encrypted I mean with this logic encryption mechanism, we make the life of the attacker much harder, because reverse engineering then is not trivial. This is the attacker not only has to understand the functionality of the original circuitry, but also has to understand how it is possible to activate the chip. The key, so the number of logic locking gates which we insert in the system doesn't have to guarantee that this mechanism is unbreakable in absolute, but it just have to make the life of the attacker hard enough so that the time window given by the time production of the chip cannot be used to reverse engineer the system. So once we receive the chip from the fab, We just have to apply the correct key and the system works normally. A bit more in detail how the hardware development flow looks like. So here we have two domains, the trusted and the untrusted domain, which are identified by the green and the red colors. We start with the RTL design, then we make a synthesis of this design and we obtain the gate level netlist. This gate level netlist is then given as an input to the logic locking tool, and the output of the logic locking insertion is on one side the obfuscated gate level netlist, and on the other side a key which is able to activate this netlist. At this point we make an equivalence check between the obfuscated netlist and the original netlist to be sure that the functionality of the system is not affected. Then we can store the logic locking key and keep it as a secret, and we can proceed with the backend design and the production of the chip. The backend design and the production then can be outsourced, so we don't have to take care, strictly speaking, also of the layout generation and the generation of the GTS2 files, but this can be performed by third-party companies. So once we receive the dies from the fab, we have to store in the chips the correct key, which at this point can be made public, and then the chips works normally. So customer don't have to take care of this anymore, and we are granted that there is no hardware trojan in them. A little bit more on the hardware platform. So I already mentioned that we are using a RISC-V based core as a processing core. Why did we pick RISC-V? Because it is open and simple, and these are key aspects when you're talking about security. And then this is a relatively new instruction set architecture, which can then benefit from the error made during the design of older architecture, and which has no backward compatibility issues. And for the other IPs we use in the design, we selected open source IPs, because this way we've been able to validate the implementation and we've been able to apply logic locking. And this gives us a base for a trustable RTL. Together with logic encryption, we are able to obtain a trustable hardware. So this diagram shows what the MiG-V offers. I will not go into the details, but just an overlook of it. So we have the Ariane core, which is our processor of choice. It's a 64-bit RISC-V architecture, which implements I, M, A, and C extensions of the standard. We have ROM in the ROM, as I will also tell later. We have not only the boot code but the SEL4 image. Then we have SRAM, which is 1 megabyte. We have a flash, which is used to store the logic encryption key. Then another security feature is the true random number generator, which is used by the software stack to set up secure connections. We have 2 Ethernet ports which support 10 and 100 megabit per second connections. We have an SDRAM interface which supports up to 64 megabyte SDRAM, and then other standard peripherals like timers, I2C interfaces, SPI and QSPI, UART, and general purpose IOs. Here I give a bit more details on the features offered by MiG-V. Regarding core and memory, I already said. Also for the peripherals, I already listed them. The system clock is 240 megahertz, and we also have a dedicated clock signal for the SDRAM up to 112 megahertz. Regarding the logic locking size, we are using a key length of 1024 bits, and this is not strictly related to the number of logic locking gates, because there are more gates used, and the drive for these gates, which exceed the number 1024, are generated internally in the system. Regarding the software platform, well, my colleagues are developing an Trustable operating system which is called Trend OS. This system is based on microkernel, and the microkernel of choice has been SEL4. The SEL4 is the only microkernel available whose features have been formally verified. So functional correctness, confidentiality, data and temporal integrity have been mathematically proven. A microkernel provides only the very basic functionalities which are required by an operating system, but the modern operating system requires also higher level features, like, for example, file system or network stack. And these complex applications are developed in user space, so they do not constitute, they are not part of a trusted computing base as opposed to the monolithic operating system, and these applications are vulnerable. But SEL4 properties guarantees that a corrupted module cannot affect the whole system. As I already said, the ROM in our system includes an image of the SEL4 kernel. The reason for this is that kernel is considered immutable. So once we perform all the formal verification proofs, then there will be no need for us to modify this kernel. So we can store it in the persistent memory, and via some validation and verification mechanism, we can monitor that the data contained in the ROM are exactly the one which we are expecting. So the ROM has not been corrupted during production. What is the status of our development? Both the MiG-V chip and the evaluation board are available. We received them in April this year from the fab. The bring-up phase has been relatively quick, I have to say, and successful. And regarding logic locking, we are actively trying to reverse engineer our design. We have a partnership with the Technical University in Munich. They are trying to break our locking scheme, and good news is that this encryption has not yet been broken. We also started testing the operating system running on top of RISC-V, so we have also the first success in this direction. And this is all from my side. Looking forward for your questions.